Okay, so welcome back. Basically, today we'll be starting on chapter 13, which is kind of like the beginning of the meat of the course. And what's funny is that uh, the most of what we did in chapter 11 and 12, so you will need all the stuff from chapter 11, of course, you need to set up all the quantities we're going to be talking about from now on. But as far as curves go, we won't discuss curves that much again until the very end of the course, where they're very important. But yeah, so those won't crop up again until chapter 15 stuff. But all the stuff we set up in that initial chapter is something that we're going to be using for the rest of the course. So what I mean by calling this the meat of the course is that the name of the course is multivariate calculus, which refers to studying functions of more than one variable, right? And so what I mean by that is in Calc 1 land, we studied functions of a single variable, f of x. Now we want to study functions of more than one variable. So functions of two variables, f of x, y. Functions of three variables, and more. Now, the thing is that once you get past three variables, typically what's done here is you would actually write these variables using subscripts. That's a lot easier than trying to come up with different letters of some alphabet. Alternatively, what would be done is writing this as f of some vector where x is understood to be a vector, containing however many variables, right? So this would be, containing n variables. This would be a function of n variables. Now, just a quick example, and you're going to get tired of me doing this because I'm going to do it a lot, because really it's the best thing to kind of keep you grounded with what you've seen before. So in Calc 1, when we talked about function of a single variable, right, the idea is you have function, and if it's a function of a single variable, you took in a real number, and it spits out some real number. Okay, and so in more advanced math classes, this function might be denoted like this, which is to say that it has, now in this case, what shows up here is the domain, so I'm showing you a function that has domain that's all the reals. It's not necessarily the case, but the point is that it has a domain that's some subset of the reals going to the real. So it takes in a real number and goes and spits out a real number. Okay, compare this with a vector valued function, right? Which, as we saw before, takes in a real number and spits out a vector, right? So all of these functions, all of these multivariate functions, are going to be real valued functions in the sense that however many variables they depend on, you plug in that many numbers, and it spits out a single real number. Okay, and so for this function of two variables, your f would take in two real numbers, so it would go from R2 from the plane, and it would spit out a real number. Similarly, this function would go from R3 to R. Again, I'm being a little loose here because technically all of these R, R2, and R3 here would be replaced with some D, which would be the domain of these functions, which would be a subset of these sets that I'm writing out. But we'll say we have a nice function in each case that's defined on all of the real line, the plane, and space, respectively. Okay. So the point is that all these are real valued. Okay. Now, what was another way an expression was written in Calc 1 whenever you had a function of a single variable, right? The first thing you're going to write out here is, y is equal to f of x. But what does this mean, right? Of course, this means that if I'm thinking graphically, I'm thinking of the graph of this function where the y coordinate is determined by the function value. So if I, oh, that is a really bad axis, right? Forget that. So if I have the graph of some function, right, in Calc 1 land, a point on the graph of that function, the coordinate is x, f of x, right? And the set of all ordered pairs x, f of x, as x ranges over the domain of that function, well, that's the graph of this function in the plane. Okay. All right, and of course, the graph of this function lies in R2. Okay, so we'll come back to that in a second. First of all, just algebraically, how do I define a function of more than one variable? Well, defining it is easy. So here's some examples. Let's consider the function f of xy. That is just x squared plus y squared. Let's consider another function, g of xy. That is square root of 4 minus x squared minus y squared. Okay, let's consider a function h of 3 variables. That is something like 5x squared minus 7y cubed plus z minus 15. Okay. All right, so here's 3 examples of functions of more than one variable. Now, if I were to ask you to evaluate, right, some of these functions at given points, you'd have no problem doing that. You just follow the algebra indicated by the functions, right? So if I ask you to plug in f of 1, 5, well, that's no problem. That's just 1 squared plus 5 squared, or 26. So f of 1, 5 is 26. Okay, so that's no issue. Now, you might think over some varying values of x and y here, and see that no matter what x and y I plug in here, I'm not going to run into any issues. I'm always going to be able to evaluate that. But immediately, you notice that for g, that's not going to be the case. Right? So for g, that's not the case. For instance, if I ask you to evaluate, right, like g of, say, 2, 1, right, then what is this? This would be the square root of 4 minus 2 squared minus 1 squared. So this would be 4 minus 4 minus 1. So this would be the square root of minus 1. Okay, which is not a real number. Right? So this point, 2, 1, does not lie in the domain of G, right? So what this little thing means is that 2, 1 is not in the domain of G. Well, question, what is the domain of G? Now, you are approaching 241 is basically one of the last math classes where a question like this is phrased in this way. So you're used to questions all the way back, to high school. You're used to questions like, what is the domain of this function? So in more advanced math classes, asking what the domain of a function is, it's a little bit of a strange question, because the way that it goes is that you decide the domain that you're interested in. The only thing is you just have to make sure that the function is actually defined, and makes sense for all those values. So really what is being asked when you're being asked for the domain of a function. You're being asked for the maximal domain, right? So if that set is, if the domain you're looking for is just a subset of the real line, you're looking for the biggest one, right? The maximal subset of the real line the function's defined on. So really what's happening is you're being asked for the maximal domain, the largest possible set the function's defined on. But when it comes to talking about the domain of a function, the domain of a function is just whatever set I've defined the function to be on. So if I take a function that is defined on all the reals, but I restrict my attention to the closed interval 0 to 1, then as long as the function's defined there, like that 0 to 1 is what I call my domain, okay? So I'm not going to get too much into that, but so when I say domain, when I ask a question like this, what I'm asking is for the maximal domain, the largest domain this thing is defined on. And so what is the maximal domain of G? So what do I need? What's the only requirement here? So obviously, since G involves this radical, the radical is the issue, so I need to make sure that this thing is always defined. But when is this radical defined? So if I'm looking at square root of 4 minus x squared minus y squared, and this is my G, all I need to make sure of is that what's under the radical is non-negative, right? It can be 0. 0 is fine. It just can't be negative. So I want 4 minus x squared minus y squared to be greater than or equal to 0. Okay, rewriting this slightly, what do I get here? I get x squared plus y squared is less than or equal to 4. Okay. So before, when you had questions of domain come up in Calc 1, you would get maybe you'd get some inequality like this, but it would only involve a single variable, which would typically indicate some interval, some half interval, some part of the real line, right? Indicated by some inequality. Here we have two variables, though. What is this? What is this the equation of? Right? Forget that this is an inequality for a second. Just pay attention to the equality part. If I wrote down x squared plus y squared is equal to 4, what is that? So what kind of object is that? Well, x squared plus y squared is equal to 4. What is that? Well, it's a circle, right? It's a circle of radius 2. Yeah, so I see chat lighting up. So that circle is the circle of radius 2, centered at the origin in the xy plane. Okay, but of course this inequality says that any point xy satisfying this inequality is fine. Well, that indicates everything inside the circle. And so x squared plus y squared is equal to 4 is the circle, the boundary circle of this region, but x squared plus y squared less than or equal to 4 is a closed disk of radius 2, is what this is called, because it includes everything, including the boundary, right? So, including the boundary here. So this is closed disk of radius 2. Now, you're automatically thinking, can I come up with examples where the domain of this function would be a open disk of radius 2? What do I mean by that? It would be this, except it didn't include the boundary. The boundary would be dashed because it's not include. You might already be thinking of an example. All you have to do there is get rid of this equality part of the inequality. And how can we do that? Just write the function g of xy is equal to 1 over root 4 minus x squared minus y squared, right? Then you're not allowed to have 0 as showing up under the radical. So that gets rid of that equality part, which gets rid of the boundary in that case. Okay. And so typically our domain D, right, is some set in the xy plane. Well, think about it, right? That makes sense because we're taking in two variables, right? In Calc 1 land, right, the idea is that we have a function of a single variable, which meant that in our plot, right, we take in some region that is a subset of R1, the reals, and that is our domain. Right, here's F. Okay, and our domain D is, some one-dimensional interval. Okay. Well, what's the analog in Calc 3 world? Well, I have a function of two variables, and so I have an x and y axis and a z axis here. And this function takes in two variables, so the domain needed to describe it, as we saw in the last example, is two-dimensional, right? So my domain is some two-dimensional set, and it can be a weird-looking set, but we'll say it's like an elliptical disk here. So here's my domain D. Right, here's my domain D. Okay, so if I have a function f and it's defined on D, what would the graph of this thing look like? Now, there's a lot of options here. If f is really, really bad, right, f could be something like a three-dimensional Christmas tree function. If you've ever seen the usual Christmas tree function, it's this bad, totally disconnected function. It's this discrete thing, like there's no connection between any of the points on the graph. But let's say we're dealing with a much nicer function than that. So if I have a function that is relatively nice, what would the graph of this thing look like? Well, maybe it looks something like this. And so this would be the graph of my f of xy. Okay. So then I would have this surface here. Now, when is it a surface? Well, it's a surface when f is nice enough. In fact, one definition that you can give of a really nice surface, one that doesn't pass over and under itself, right, is as of the graph of a nice enough function of two variables. Okay, so it's this surface-looking thing. Okay, so an individual point, of course, here, an individual point on my function was some x, f of x, right? Whereas, and below I had my point x, right? And so here's x, f of x. So then if this is a generic point xy in the xy plane, right, xy 0, if you like, then an individual point here on this graph would be x, y, f of xy. Okay. Of course, so Dylan, yes, that's a good thing to notice. The graph is in 3 dimensions even though it has 2 variables. So notice that here, how many dimensions did it take to graph my function of 1 variable? Right? It took 2. So you're already used to this pattern, right? Is a surface a 3D object? Okay, so here's the way that this goes. A surface is technically a two-dimensional object. And the reason why is when we speak of the dimensions of an object, we don't consider the ambient space it sits in. That might seem silly, but there's a very good reason for that. Unfortunately, I can't totally get into why we can do that because it would take too long. But the point is, when you consider the dimension of some object, you can consider just the object itself. You don't have to think about where the object is sitting, okay? Just because it's interesting, I'll mention it. There are surfaces, okay, that you cannot sit in R3. Okay, there are surfaces that cannot be embedded in R3 in a nice enough way that is an accurate representation of them. If you're looking for examples of this, the Klein bottle. Okay, Klein bottle is an example. If you've ever heard of a Klein bottle, you might have even seen some representations of a Klein bottle. So a Klein bottle is an example of a surface that is not too hard to describe mathematically, but you can't actually put it into space without it not actually being the Klein bottle, because it intersects itself in space. So you would need one more dimension. You'd need 4 dimensions to be able to accurately sit it in space. Now, the point is that none of that matters because the surface itself is dimension 2. The easiest way to see that a surface is dimension 2 is you restrict yourself. You think that you're an ant on the surface, right? So think of being an ant on the surface of a sphere. So a sphere is an example of a surface that is not the graph of a function of 2 variables because it passes over and under itself. Okay, and I haven't even written the definition of a function of 2 variables, but it's the same idea as a function of 1 variable. A function has to satisfy this property that there's no ambiguity in values. The second that you specify an x and a y, there's a single f of xy. Okay, there is no, like, oh, there's no choice, right? So in this case, if my domain was this, disk passing through the center of the sphere, if I pick a point here, right, which would be the point that I pick, the one up here or the one down here, right? There would be a choice, okay, and that's not a function. Now, we're going to see there's a perfectly fine way of writing a sphere as what's called a parametric surface. Okay, and of course we have no problem writing upper hemisphere, lower hemisphere. We'll do that here in a second. Okay, Dylan, yes, exactly. So a 3-variable function would have a graph that's 4-dimensional. So have fun visualizing it, right? That's right. And anything higher dimensional than that, you're increasing the dimension by 1 every time with this graphing notion. To see that a surface is 2-dimensional, imagine I'm a bug living on the surface of a sphere. Of course, remember, don't get confused here. The sphere is the outside, right? The sphere it's the outside of the sphere itself. It's not an inside. It's not a solid ball. Okay, you can't access the inside of the sphere. Now imagine you're wearing like magnetic boots or something. So there's no jumping. Okay, there's no getting off the sphere. You're on the sphere. Okay, so how many directions can you go? Well, you can move this axis of direction, and you can move this axis of direction, and combinations of those, right? But nothing else. Okay. All right, so nothing else. So the point is that you have 2 dimensions worth, right? At every point on the sphere, you have this locally, you have the plane, basically, that is showing you what's going on here and how many dimensions or how many directions you can move. So it's 2 at each point. So the sphere is 2-dimensional for that reason. Okay, so surface is 2-dimensional, but to graph a surface in this way, we need 3 dimensions. Okay, and as someone noted, yes, if you were trying to plot, the graph of an f of xyz, this would require 4 dimensions, right? The graph of this would require 4 space. So 4 space. Okay, which I'm not going to draw. Okay. Yeah. Okay. Corey, it wouldn't be the normal vector because the normal vector to the surface would stick like straight up. So you're hinting at an issue here where when you have a curve, talking about the tangent normal vector is something we know how to deal with. But when you have a surface, now it no longer makes sense to talk about tangent vectors on their own. Why? There's too many of them, right? Imagine a sphere that's some ball sitting here. If I talk about the tangent vector at the North Pole of the sphere, well, there's too many choices, right? In fact, there's all those, right? So imagine let's see, do I have anything sitting here? I'm looking around the room. Do I seriously not have a single? Okay, well, we've got empty Mountain Dew cans, which is, we can consider the exterior as a surface. So here's an empty Mountain Dew can. If I consider this as, cylindrical surface, then at this point here on the can, that's a tangent vector to it. Okay. But what's also a tangent vector to it? That one. And that one. And any of these, if I take this and I just spin my pen, all of those are tangent vectors. So talking about the one-dimensional object, the tangent vector, is not going to be that helpful because there's just too many to pick from. But what am I doing there when I'm rotating through all those tangent vectors? I'm showing that there's an entire tangent plane. Okay, so there's an entire tangent plane to that Mountain Dew can. So for instance, if this is a plane, right here, you can't hardly see it because I'm covering it up, but this piece of paper is the tangent plane to that thing at that point. Okay, so we'll talk about that in a couple sections. That's going to be one of the main first things we do computationally. Okay, all right. What is a multivariate function? So a multivariate function is a rule that assigns to each point in its domain a real number, and I should say a single real number. Okay. Now, of course, the point here, right? So if D is two-dimensional, if D is 2D, that's a funny statement, i.e., what we mean by that is our subset of D lives in R2, the plane, then the function we have is some f of xy, right? If D is 3D, i.e. D is contained in R3, then the function we have, this is a stupid statement then, and then I just write this, but I'm using words to be more efficient here. Okay. And so on, right? And there's no stopping here. You can consider a 17-dimensional domain. There's no problem with that. Okay. And so the number of variables tells you how many dimensions the domain is, right? So 2 variables is 2-dimensional domain, 3 variables, 3-dimensional, and so on. Okay. So then the first question is, first big question, and this is because obviously in this course we are going to be concerned with things that are fairly nice and are nice computationally and visually, and so the immediate thing that we're going to do is tie them in with their graphs, which is what you did in high school, right? When you talked about functions. Period. One of the first things you do with functions, or one of your first examples, is plotting them, graphing them, right? So first big question is to figure out what some function f of xy looks like, right? Just from its algebraic form. Now, this is not going to be something that you're going to be super successful with for a completely general function of 2 variables, because even a really, really simple function has an absolutely, can have an absolutely god-awful graph. So even something like, there's an example in the textbook of sine x plus sine y. Um, like even something like, so note, we can't be mega successful here. Consider f of xy is sine x plus sine y. So this, you would think maybe in your head that this would be like an easy thing to plot, but it is not at all. It's complicated looking. Now, conceptually, it's not that hard to understand what this thing is doing, but the actual plot of it looks messy, and it's not something I could accurately draw at all. Okay, so let's do some examples of trying to understand what's going on here. So the first example we'll do is f of xy is x squared plus y squared. Okay. So, quick question. What is maximal domain D? All right, so question, what is domain? What is my domain for this function? Well, this function is a polynomial in two variables. Okay, so you know what a polynomial is in a single variable. Polynomial in two variables is just, you consider a polynomial in x and a polynomial in y, you've smashed them together like this, right? So the types of things that are allowed are the polynomial type terms. Okay, and the nice thing about polynomials, of course, is that all polynomials were defined for all reals, right, in Calc 1. Of course, in addition, they were all infinitely differentiable, which meant they were all continuous, blah, blah, right, all kinds of nice facts. But here we have polynomial in two variables, and so a lot of that exact same stuff is going to carry through. That polynomials in two variables are really nice. There's no restrictions here. I can plug in any x and y that I want, and so if I'm asking for the maximal domain, it's just all of R2, right? It's just the entire plane, right? So the entire plane. Okay. All right. And so that's another thing here, right? So let me go back before I continue on. So in this previous example, because in Calc 1 world the y coordinate was determined by f of x, we would write frequently y is equal to f of x. This would be our way of indicating that we were considering the graph whose y coordinate was determined by this function, or the graph of the function f. Here it's our z slot that is being determined by the value of the function. And so, for a function of two variables, what is frequently written is z is equal to f of xy. Okay. So this is just our way of indicating that we're considering the graph, right, of the function f of xy here. So that means the z coordinate is determined by the value of f on x and y. And so another equivalent way you can see this written is z is equal to x squared plus y squared. Okay. Okay. So its domain's the entire plane, so we can plug in any point on the entire plane here. And of course, if you just start plugging in some points, f of 1, 3 is 1 squared plus 3 squared, so that's 10. And f of, say, 5, 10 is 5 squared plus 10 squared, so it's 125. Okay, well, I can't really determine anything in this way, right? In fact, if I just start plugging in points, this is the worst possible way to understand how the graph of something looks, even in the plane, right, where we have one less dimension and things might seem a little bit more nailed down. In space, right, imagine Imagine how terrible it would be in space to actually plot individual points and try to see what a thing looks like, right? That's clearly not going to be the way to do it. Okay, so what do I do? Well, my first idea is to consider, if I'm thinking of this being, this is going to be some surface. Someone is saying circle with radius square root of z. The problem is that I don't really know what the square root of z is doing there. You're not wrong that this is essentially what we're going to be doing, but since that z is going to change, right? I mean, you see how my z is going from 10 to here it's 125, and it's just going to get bigger and bigger and bigger. What you're saying in the chat, though, is essentially what it is I want to do, at least partially. So this is partially what I want to do. This will take care of 33% of what I want to do is this. Well, Mikhail, it's not a helix, because a helix is one dimensional. This is going to be a surface. And it's not going to be what's called the helicoid. The helicoid is an example of the helix made into a surface, but the problem with the helicoid is that it passes over itself, so it's not the graph of a function. Because there's infinitely many points above and below that point, so there's no way of nailing down what thing you're talking about. Yeah, the helicoid's a 3D, is a helix made into a surface. That we will do. We will do that in chapter 14. We'll talk about the helicoid. Isn't it like a big cup? Kind of, sort of. But how do we see this? The main idea, is to consider cross sections of the graph of f of xy. Now, what is a cross section? So a cross section is, if I imagine I have a three-dimensional object, so let's bring back my Ducan. Okay, so if I imagine I have a three-dimensional object like this, now this Ducan tapers off at the top, but imagine it didn't. Imagine that it was a perfect cylinder. I don't have any Red Bull cans here, but imagine that it was a perfect cylinder I was holding here. A cross section of this thing, one example of a cross section would be I consider a plane cutting exactly perpendicular to the can like this, in this direction, cutting through the can. The intersection of the plane with this cylinder forms what geometric object? Well, to see that, I would have to look directly at the can, and of course it would form a circular cross section. Okay, and so the cross section with a plane cutting through this cylinder in this direction would yield circular cross sections. But what shape would I get if I considered a plane cutting through the half of the can like this? Again, imagine that this didn't taper off and this was a perfect cylinder. What cross section would I get cutting a cylinder like this? You can tell me in the chat. If you cut a cylinder in this way, a perfect cylinder, it doesn't taper off or anything, what shape do you get if you cut it that way? Oh, I almost picked up the full Ducan. That wouldn't have been good. A rectangle, exactly. So chat said it. You would get a rectangle. So in one direction, you would get a rectangle. In another direction, you would get a circle. And so you can see how even for something like the cylinder, cutting through here, I get a circle. Cutting through here, I get a rectangle. And you're like, how do I put those together? Well, if I had a bunch of different cross sections, of course, I could consider planes coming in at any angle to see what kind of thing I would get. It just helps me get an idea. So the idea is that I want to consider cross sections. That is, I want to consider planes intersecting this graph. So i.e., I want to consider the intersection of the graph, intersection of some particular planes with the graph of f. So you're sitting in space, right? And let me put a label on it, of course. So here's space, what are some planes that you notice that are nice to consider? So what planes in question are nice to consider for this property? Well, there's the xy plane, there's the yz plane, there's the xz plane, and then there are planes parallel to all of those that I mentioned. Those are nice planes, right? They're not coming through at angles or anything like that. So let's consider the intersection of the graph of f, right? So let me rewrite this. So get rid of this for a second. So let me rewrite my function. So it's x squared plus y squared. Okay. And so let's consider the intersection of the graph of this thing with some planes. So let's choose the plane, let's choose the yz plane. Okay. Okay, so let's choose the yz plane. Well, on the yz plane, so here's my graph of space. If you're thinking of a corner of the room, the yz plane is this wall, right? It's this wall back here. Well, on the yz plane, like, what's the best way of like writing out algebraically what the yz plane is? It's the collection of all points in space, x, y, z, such that what? Well, such that x is 0, right? It's the points such that x is 0. The yz plane can be written algebraically as x equals 0. Okay. And so on the yz plane, what does the graph of my function look like? Well, when x is 0, all right, so f on the yz plane is really f of 0y, which is 0 squared plus y squared, or y squared. And so my cross-section with the yz plane, what does that look like? So here's y, here's z. What does this cross-section look like? What does f of y is equal to y squared look like? It's a parabola. All right, it's your favorite parabola. So this is f of 0y is y squared. Okay. Okay. Well, what about the xz plane? So that's this left wall oriented like this. So what about this left wall? Well, on the xz plane, of course, that's the collection of points x, y, z in space such that y is equal to 0. And so on the xz plane, my function is f of x0, which is x squared. And so similarly, if I plot this in 2D, xz, the picture I get is parabola. You might say, is this the same parabola as this? No, right? This one is oriented like this, and that one sits here. I'll draw both of them in here in a second when I'm actually sketching this. Okay. And so this is, oriented differently. This is the xz plane. Okay, so this is f of x0 is equal to x squared. Okay, now you might check the xy plane, but notice that on the xy plane, so the xy plane is z is equal to 0, right? So the xy plane, that's z equals 0. But if z is equal to 0, what is that? That is my height, but that's z is determined by f. So this is 0 is equal to x squared plus y squared. But what is that? If 0 is x squared plus y squared, what's the only possible way this can happen? Both of these have to be 0. And so the xy plane only intersects the graph of f at a single point, right? At the origin. Okay. So then it's not enough to just use the xy plane. I want to use different planes that are parallel to the xy plane. So then my next idea is to use planes parallel to the xy plane, which of course is the plane z equals 0, at varying heights. So at varying heights, and we can determine those heights by saying, we call those heights z equals c, where c is some positive constant. Okay, so the plane z equals 1, z equals 5, z equals 17, those would be planes that are parallel to the xy planes at height, 1, 5, 17. And so let's try a few different ones. So what about z is equal to 1? Right? Well, if z is equal to 1, this means that 1 is equal to x squared plus y squared. What is this? So this is a circle of radius 1. This is a circle of radius 1 centered at the origin in the plane z equals 1, right? So I'm not going to write that for the rest of these. So centered at the origin in the plane z equals 1. What about if z is equal to 2? Well, then I get 2 is equal to x squared plus y squared. So this is circle of radius square root of 2. Right? And z is equal to 4. This is 4 is equal to x squared plus y squared, which is circle of radius 2. And so, as someone said in chat earlier, each of these are just circles of varying radii determined by the height. So whatever the height is, the radius of the circle is the square root of that. Okay. Okay. And so if I actually were to draw these, right? So here, this would be a circle of radius 1. Here would be same picture, but it's circle of radius root 2. And then here, same picture, but circle of radius 2. If I put them all on the same plot, understanding that they are in different planes, right? So this one's in the plane z equals 1, this is in plane z equals 2, this is in the plane z equals 4. What if I project down, right? What if I project down, right? So I'm looking directly from the z-axis. So imagine the z-axis is here. Okay, so here's my z-axis pointing directly up at the camera. Okay, and I take all these curves in varying planes. So z equals 1 is like at this height, and that's my circle of radius 1. And then I go a little bit higher, and then I would have a circle of radius root 2, and a little bit higher, I'd have a circle of radius 2. Imagine I push all those circles down into the xy plane. What does the picture look like? So here's my circle of radius 1, here's my circle of radius root 2, and then radius 2. Okay. Okay, now those are really bad circles, but anyway. So this is what my picture would look like. What is it that's going on here? In each of these cases, when I specify a height, notice I get a curve, right? I get some curve, okay, that is specified by this height. Okay. What are these? And where might you have seen this before? So these are level curves. These are level curves for the graph of my function. These are level curves, so f of xy equals C, this is an example of a level curve where we're picking different values of C here. So we picked C equals 1, C equals 2, C equals 4, and this is what we got, right? So this outer circle was for the choice C equals 4, this was for the choice C equals 2, and the inner one was for the choice C equals 1. Okay. All right. And so this is an example of a level curve. What is a level curve? It is just the intersection of a plane cutting through the graph of f of xy at various levels. The level is the height determined by C. Okay. All right. Where might you have seen this before I go back to our original problem? So when I was like 4, I was obsessed with maps. So I was obsessed with atlases. And my grandmother had this gigantic like atlas from like 1912 that was this massive, huge tome. The book was so huge I couldn't even carry it. And it was just a book filled with maps. And so it was like every single country and region in the world, plus multiple types of maps, right? And so maybe you would have the map of a region, and that map would look like this. All right, what is this? So what is this a map of? All right, maybe it looks like that too. Yeah, so this is a topographical map, but what is it that's being drawn here? And you may have some like things noted here, right? So you might have like, we'll call them, this is like C is equal to 100. This might be like C is equal to 120, and this would be like 130, right? Here, and this would be 140. What is this? It's elevation, right? It's elevation. And so the idea here is that imagine that the topographical layout, right? Imagine you're looking at some mountainous region and you're making it nice, smoothing it out, and saying that that is like some surface, right? So that you can view that as like the graph of some surface sitting in space. If you imagine these levels, right, at various, so z is equal to 100, z is equal to 120, 130, whatever, cutting through that mountain, right, parallel to the ground, right, the xy plane here, then what you get would be curves. And maybe because the mountain, has peaks and valleys all over the place, maybe you would get disconnected sets of curves, right? In our example, we didn't get that, but you could get disconnected sets of curves. So maybe at c equals 100, you get this here and also this here because there's peaks. Okay. The idea is that this would tell you the elevation. So if you specify the level of the level curve that you get, or the level of that plane cutting through parallel, you would get varying heights here determined by these level curves. So an elevation map is an example of where level curves come into play. So this is like a specific example of level curves. So anyway, let's draw this and then we'll be done for the day. So I want to sketch the graph of x squared plus y squared. In the yz plane, it's the parabola y squared. In the xz plane, it's the parabola x squared. So in the yz plane, it is this parabola on that wall. In the xz plane, it's this other parabola. Trying to draw with perspective now. Okay. In the xy plane, it only touches it at that point. That's right. And then we have these levels, right? So at each level, it's a circle of increasing radii. So here at this height, it would be a circle, and it would be a circle of slightly bigger radius here, and a circle of slightly bigger radius here. Of course, if I push all of those radii, if I push all of those levels down, so this is the, this is at height, we'll say c equals 1, this is c equals 2, this is c equals 4, even though that doesn't scale at all. If I push all those down into the xy plane, all those circles would appear down here. Appearing on the graph itself, that's what they look like. So what is this? This is almost, it's like a parabola, but when you look at cuts of it, you get circles. This is an example of a thing called a circular paraboloid. Okay, circular rather than say like elliptical more generally or some other shape, because at every level or at every slice, right, that is parallel to the xy plane, all my level curves are they're circles, not ellipses or anything more general. So anyway, so this is what the graph of this thing would look like. We'll do a couple more examples of that next time, and then go on to how we are going to compute with these things. Okay, so we'll very quickly get into the computational aspect, but it's good to see this stuff kind of nail down what it is that's going on here. Okay, so anyway, I will see you all on Wednesday, and your exam, if you haven't turned it in yet, is due tonight at midnight, so don't forget that. No, Rashmi, no, none today, but if you have any, email me, and I'll be on my email all day, and I will quickly respond. Okay. All right, so I will see you all on Wednesday. Kira, I'll look right now. Okay. Yeah, I'll look right now. I'll respond to you here in like 5 minutes. Okay. All right. So anyway, I'll see you all Wednesday.